Okay, so 2-2 starts to really get a sense, chapter 2 in general, um, what you're going to find in a calculus class. So the first thing we're going to talk about is the limit of a function. We had introduced limit notation last year a little bit when we talked about end behavior, but in this section we're going to talk about what it means to talk about a limit. Limits are super important. Without limits, we couldn't do some of the formulas that we'll have later on. So, let's see here. So they do become an important part of everything that we're going to do. Okay. So yesterday, when we looked at things that we were trying to find that slope of that tangent, that notion of getting super close to something. If you notice, if we plug 4 into this function, or I'm sorry, 2 into this function, we approach a height of 4. So like here, 1.999 gave us 3.9970001, super close to 4. But if we plugged in on the other side of 2.001, we still get a number super close to 4. So what this notation means is as we approach 2, so you would read that the limit as x approaches 2. The limit as x approaches 2. The function value approaches 4. That's what that wording means. The limit as x approaches 2, the function approaches 4. Now, this is a polynomial, which has no breaks or jumps. Last year we learned polynomials didn't have any issues with them. They were this lovely, wonderful curve that didn't have any holes or breaks or discontinuities. So in this particular case, the height at 2 is exactly 4. We are going to have some functions where as we get super close to that value, we're going to approach a certain area or a certain height, but we don't necessarily land there. A limit is not saying that we land when x equals 2, that we land at 4. It is saying we are approaching a height of 4. So you'll notice here, as I come in this way, I am approaching a height of 4. As I come in this way, we are approaching a height of 4. So it's a little different kind of thinking, that limit notation, because not all functions land where they approach, because there could be a hole there, there could be a gap there, there could be an issue there. Okay. So if you look at these functions, all of these limits, I'm going to write this a little bigger. It's saying the limit as x approaches a of this function, they are all approaching a height of L. Okay, now let me zoom in for you a little bit, and you have this too. This function approaches a height of L from both sides. That's why that limit as we approach an x value of a is L. This one, as we approach from both sides, we are heading to a height of a, or when we approach x of a, we're heading to a height of L. Do we land when x equals a at a height of L? No, we've got this point down here. So the limit still is L as we approach a, but we're not landing there, okay? Or you could just have a function that is undefined there, but as we approach it from both sides, we are heading to a height of L. We don't necessarily land there. So a limit is saying, what height are we approaching from the sides? Do we land there? Maybe, maybe not. But that's not a concern of a limit. A limit is just what are we approaching from both sides? Now you'll notice for this to have an answer of L, you'll see, both sides are approaching the same height. That doesn't always happen either. Think of our piecewise functions. We may have an inconsistency. So we will address when it sometimes works and it sometimes doesn't. So just a little thing to think about as far as the notation goes. So example 1 here. What does it mean if the limit as x approaches 1 of f of x is 3? All we are guaranteed is that as we approach x equals 1 from both the left and the right, it's heading to a height of 3. That's all we know. As we approach x equals 1 from both the left and the right, it's heading to a height of 3. So if we looked at the graph when x equals 1, all we know is that the left side's heading to 3 and the right side's heading to 3. I don't know anything else. It might not be defined at that point. It may be defined. It might. I don't know. Okay. Now, some new notation for you. So I'm going to write this notation at the top. If we say the limit as x approaches a, and we put a little minus there, that notation means we are looking at the height from the left side. So I think negative should indicate to you a little bit less than what I am approaching. If I put next to the value a little plus sign, that is the height from the right side. If they don't specify, like in A here, that means we are going to a height of 3 from both sides. If they don't specify, both sides are heading to that height. But if they put a little negative notation or a little positive notation, they are only saying as I come in from the left side or the right side. So the negative notation means from the left side. Positive means a little bit more than that. It's coming in from the right side. Okay, so that's important that you know that notation because that notation is going to come into play. So let's look at part B here and how part B changes things up a little bit. Okay, so let's look. So we are heading to a height or an x value of 1. What this notation says is from the left side, we are heading to a height of 4. So I'm going to make a very generic picture here that from the left side, I'm heading to a height of 4. Okay. The little plus notation means from the right side, I am heading to a height of 6. I know nothing about anything else about my function. This side could go way up here, this side could go way down here, this side. All I know is at that little juncture right there, the left side is coming into a height of 4, the right side is coming into a height of 6. That's all I know. So it says, does the limit at 1 exist? Well, that notation means that both sides are going to the same place. Are both sides going to the same place? No. This is a discontinuity. Remember last year we had 3 types of discontinuities. We had a jump discontinuity, we had an infinite discontinuity, and I don't know what the other was. We'll think about it in a second. But we had different types of discontinuities. This one is a jump discontinuity. Something's wrong there. Okay. So does that exist? No. These sides have to match. If they don't match, the limit at that point doesn't exist. Because which do we choose? Do we choose 4 as the right answer, or do we choose 6 as the right answer? I don't know. Yes. So for a limit to be defined, and I think that's what maybe the next page says, both the left and the right have to match. So you'll have to have both the negative notation and the positive notation going to the same value for it to work. And I think that's what the next one says. Yes. So we have this one-sided limit here. This is the left-hand limit, like I told you. The negative notation means we're coming in from the left. The positive notation means we're coming in from the right. And the limit exists if and only if both the left and the right match. The limit will equal L as we approach A only if both the left-hand side and the right-hand side match. There are some functions like a square root function. Some functions like a square root function will only have, you know how it only has that swoop to the right for the traditional parent square root function. It only has a right side. It only has a part to it. So there are some values that won't work. There are some times we have a left end, not a right end. We have a left side a limit. We don't have a right side limit or whatever. It just depends upon the function. So that's why this notation came into play, because of the fact you have to check it from both directions. The left side, the right side have to match, or the limit at that point doesn't exist. So the left and the right side have to match, or the limit doesn't exist at that point. So there is a function. This is kind of like a switch. We think of it as an on and off. You might recall in some type of electrical applications, you kind of think 0 as an off and a 1 as an on sort of thing. So this is called the Heaviside function because it was named after an electrical engineer. So this function is 0 for anything less than 0. So it would look initially like that. And then it's 1 for everything that's greater than or equal to 0. So it's a piecewise function. So it has that horizontal line at 0 for everything negative, and a horizontal line at 1 for everything that is positive. So then the question that we're pending here is, what is the limit as, they use t, I didn't use t in both places, but we'll assume the x is the t. What is at time 0 if we approach it from the left? Well, if we approach it from the left, what height are we stuck at? It's 0, right? But if we approach it from the right, what height are we stuck at? We're stuck height. We are stuck at a height of 1. So if we say, what is the limit as x approaches 0 at the Heaviside function? Let's use x here. We would say that it does not exist because of the fact that our limit from both sides is undefined. Hi. So be careful. As to what they've asked you, if they ask you from a left side limit or a right side limit, you might get an answer. This one I am approaching from the left, a height of 0. This one I'm approaching from the right, but I'm going to a height of 1. But the actual limit without that little plus or minus on it does not exist, because I don't know which is the right one to pick. Yeah, am I at 0? Am I at 1? I don't know. So that happens a lot with piecewise functions. That can happen with piecewise functions. Okay, does that make sense? Yes. So if I am approaching, if you see that little negative notation, that means I am coming in from the left-hand side of 0. So here's an x value of 0. I am coming in from the left. And then this means I am approaching an x value or t value of 0 from the right-hand side. So that would be this. Okay. So the negative notation, you start from the left of that value and swoop in. The other one, you start from the right of that value and swoop toward that value. So please, for a piecewise function, especially the border value of a piecewise function can have issues. So now let's look at an example here. It says, for the given function f, state the value of each of the given quantities if it exists. If it doesn't exist, let's explain why. So we've got this piecewise function, okay? So let's look at this first notation. So it does not have a little plus or minus next to it. Yeah. So it is asking you, as I approach a height or an x value of 0, what is the height of my function from both sides? So here is an x value of 0. From both the left side and the right side, I am approaching a height of 3. The answer is 3. Okay, now let's look at this one. It has that little negative notation, so we're going to approach 3 to the left of 3. So like at 2.999, you know what I mean? Okay, so here's our x value of 3. As I approach it from the left side, what height am I heading toward? 4. Now C says, with the little plus notation, that I am heading there an x value of 3 from the right-hand side. What height am I heading to there? 2. Does the limit exist? No. The left side value and the right side value does not match. The limit does not exist. Just put does not exist. Okay. But the limit doesn't exist. But does the function value exist? Yeah, it's this point right here. What is the function height at 3? It's right smack in the middle of that. It's 3. So watch what they've asked you. If they do not specify, we have to come in from both directions and match the same height. So this one has to match from both sides of 0. This one has to match from both sides of 3. But this little notation means I'm just coming in from one direction. This means from the left of 3, less than 3, left, less than. So I'm coming in here. But this one means from the right of 3, so I'm coming in from there, okay? Everyone good with example 2? Okay. Now let's look at example 3. We have lots of them to do here. We're just going to take one at a time. You will notice that A, B, C, and D are all focusing on an x value of negative 2. We're looking at an x value of negative 2. Okay. So this first one here, so those all go together. So let's focus on these ones together. So all of those are using an x value of negative 2. What does this notation tell us? What direction are we coming from? The left of negative 2. So here's an x value of negative 2. As we come in from the left, what height are we approaching? Negative 1 down here. Be careful. This is the x and y axis. I have found on this graph paper where I got these examples, it's sometimes helpful just to kind of highlight the x and y axis just so that it pops out at you. Okay, so we are heading to a height of negative 1. But what height are we heading to if we come into an x value of negative 2 from the right? We are heading to a height of 1. So does the limit as we approach negative 2 exist? Look at how these answers, this one is negative 1, this one is positive 1. Do those match? No. Okay, so remember, the limit at the point has to exist, or will exist only if this height and this height match, and they sure don't. One is at negative 1, one is at positive 1. Nope, don't match. So just put does not exist or the null set. But is the function defined at negative 2? Yeah, it sure is. It's at the height of 1. Okay, now for E, F, and G and H, we are all going to be focusing this time on an x value of positive 2. Okay, so we want an x value now of positive 2. So we're focusing on this area right here of the graph. Now it's a little hard to see, so I'm going to kind of color it in a little bit, just so you get a sense of what's happening. And this is just a little like a squished in sine wave, okay? That's a squished in sine wave, just so you know. Okay, so if we look at our first one here about an x value of 2, where are we approaching 2 from in E? Where are we approaching 2 from in E? From the left. So as I approach an x value of 2 from the left, what height am I approaching? 1. Now, F has that little plus notation, so it means I'm coming in from the right. If I come in from the right side, what height am I approaching? 2. So does the limit exist? No, because E and F do not match. That's a does not exist. Okay, but is G of 2 defined? Do we have some kind of closed-in dot at an x value of 2? We sure do. This is a closed-in dot. That answer is 2. Now, I and J go together. I and J sorry, I'm going to get some cuter colors here. I and J are both relying on an x value of 4. An x value of 4. Now, I'm going to zoom in here. Let me erase my stuff so you can see it a little better. Okay. If I zoom in here, if I'm coming in from the left side, what height is that? Can anybody tell me? It's a height of 2. If I'm coming in from the right side, I know it's wiggly and it's going, but what height am I heading toward? Aren't I also heading to 2? I'm getting there in a wiggly path, but I'm still going to a height of 2. Although they didn't ask, and I wish they would, the limit as x approaches 4 of our function is 2. It is heading to a height of 2. Do we land at a height of 2 at 4? No, it's an open circle. So g of 2 does not exist. So there's one where the limit exists, but the function value doesn't exist. So be careful as to what is happening. And then finally, K and L are both talking about 0, an x value of 0. Okay. Is g of 0 defined? Nope, there's an open circle there. So that's a does not exist. Okay. But as I approach 0 from the left and from the right, because remember that notation doesn't specify, am I heading to the same place? Yes, what am I heading to? 0. So the answer is 0. So there is example 3. So limits are a little bit strange to think about. The little negative next to the number as a superscript means I'm coming from the left. The positive means I'm coming from the right. If there is no notation like that, you are going to have to come to the same height from both sides. Are there any questions about that example? Okay. What you'll find about the new stuff we're going to get to, the calculus stuff, it is not necessarily super difficult. It's odd. The notation's different. The thinking is a little different. It's a brain exercise. And I'm sorry this came out so weird. I don't know what yours looks like. Can I see yours? But it does. Oh, it's still weird though. Okay, let me kind of highlight what it should say and then we'll talk about it for a minute. Okay, so one of the things I talked about is that back in pre-calc, we had some discontinuities, some problems with the graphs. In the piecewise functions, the pieces might not come together. If there's a vertical asymptote, we call that an infinite discontinuity. One side's going to go up or it's going to scooch down. You know, think about a vertical asymptote, what that looks like. So let me kind of highlight so you can read this. I don't know. Look, it's like appeared like 2 or 3 times. I have no idea what happened. Don't ask me. Can't tell you because I don't know. Okay. So as we approach a vertical asymptote, the limit as we approach that vertical asymptote at some x value of a will always either be positive infinity or negative infinity. That's what you want to take to it, okay? So let me just kind of write it out a little nicer. So if x equals a is a vertical asymptote, we learned about those last year. It's usually where our function is undefined, especially for fractional functions, rational functions. If x equals a is a vertical asymptote, the limit as we approach a is either going to be positive infinity or negative infinity, one of the two. And then I'm going to show you as we do those, I'm going to show you how we can pinpoint that, okay? So that's the main thing to remember, that if x equals a is a vertical asymptote, the limit as we approach a is either going to be positive infinity or negative infinity, depending on what the function is doing. So this occurs in rational functions like 1 over x plus 2. There's going to have this happen wherever your denominator equals 0. So yeah, so just make sure you write this down. Okay, vertical asymptotes, if we approach them, we're going to go head to positive or negative infinity. So let's look at a perfect example. Let's do f of x equals 1 over x plus 1. Now, you may recall that there is a vertical asymptote in a rational function where our denominator equals 0. So if you just set your denominator equals 0, we have a vertical asymptote at negative 1. So the first thing I'm going to put on the graph is a vertical asymptote. I don't know why it's not letting me choose it, but never mind. Okay. You may recall that these have a horizontal asymptote at 0. If you plug in 0, you get 1. If you plug in negative 2, you get negative 1. And so it looks something like this. Okay, so that's what our graph looks like. So last year we did these. We will review rational functions when we need to, but let's talk about limits. So let's find the limit as x approaches negative 1 from the left. Let's find the limit as x approaches negative 1 from the right. I'm going to have to split you guys up during notes because you guys talk too much. We're not done. We're not done. Fine. Okay, and then we're going to do the limit as x approaches negative 1. So we're going to go from the left, go from the right. We're going to see what happens, okay? So let's think if we approach negative 1. That's our vertical asymptote. And let's approach it from the left. So we're going from the left. Are we ever going to land there? No. But what height are we approaching? Negative infinity. Okay. Gosh, I'm having problems writing today. So now let's approach it from the right. Bam, 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 bam. What height are we approaching? Positive infinity. Now, if they matched, that would be our answer. Even for infinity answers, if they match, that's your answer. If they don't match, it's a does not exist. So if they both said positive infinity or both said negative infinity. So when does that happen? If you had 1 over x squared, it goes like that. They both go in the same direction. That would be an answer where they match. If it's a traditional 1 over x plus something, if there's an odd number of them instead of an even number of them, it's going to do opposite directions. So that's a strange one where our answer is positive or negative infinity. We will talk about as we approach positive and negative infinity, that's something different. But if we approach a vertical asymptote, your answer is either positive infinity or negative infinity. If they match, that's your answer for both. If they don't match, you don't have an answer at that spot. Does that make sense? Kind of, maybe. Okay, so as we came in from the left, we went down to negative infinity. As we came in from the right, we went up to positive infinity. But since those don't match, we can't say there's anything good happening at negative 1. Okay, so as we approach vertical asymptotes, many times you will see they will split it up and they'll say, what's the negative? Where are you approaching from the left? Where are you approaching from the right? They don't expect that they'll always match because they very, like half the time do. Okay. If you can read that, I apologize. So you really kind of just need this portion right here. Yeah, because these mean the same thing. As we approach it, it's just saying from the left or from the right, we are going to head to positive or negative infinity, depending. And we're going to explore how do we know, what's the difference. But yeah, make sure you have that down. That's the main thing you want. No, yeah. It's either positive infinity or negative infinity, depending. Sometimes it's positive, sometimes it's negative, as we saw. It's very common, yeah. Okay, so here are some vertical asymptotes to look for. So this would only be from the left. You'll see this one as I'm approaching A from the left, I'm going to positive infinity. Here's I'm approaching A from the right. That's what it would look like if I approach it from the right and get a positive infinity answer. And there's what the negative infinity answer looked like. So that's if I'm approaching from the left, going to negative infinity. Approaching from the right, going to negative infinity. The only time you get an answer at a vertical asymptote for both sides, they both have to match. So they either both have to go up or they both have to go down. Okay. And then let me scroll up so you can, here's the first two. So that's going to positive infinity. So that's an example coming from the left. That's an example coming from the right. So we sometimes refer to that as a one-sided limit. It works from one side. Sometimes there's not even a piece on the other side like these ones. Here is coming from the left going to negative infinity, coming in from the right going to negative infinity. So we are approaching A from the left, but going down to negative infinity. Approaching A from the right, going to negative infinity. And then the bottom examples are where we're approaching A, and because both sides are going up or down, you get the appropriate answers. So this one goes to positive infinity at A. This one goes to negative infinity at A. And you only can say that if both ends are heading to the same location. If one goes up and one goes down, you can't make that claim. So that's just what they look like, just so you have that as a reference. So let's do some here that have some infinity limits. Okay, so I want to do E first. So I'm going to focus on this part. See where it says the equations of the vertical asymptotes. So I am going to put in the vertical asymptotes, and I'm also going to, I'm going to put in the vertical asymptotes, and then I'm going to draw them in too. So first, I'm going to highlight the X and Y axis just so they're a little clear because this graph paper is weird. So I apologize, but okay. So let's put on our vertical asymptotes. Okay. There's a vertical asymptote here. The equation of that is X equals negative 3. So I like just kind of putting them right on the graph paper. It's just nice. Then I'm going to draw this one in. And that's it at X equals 2. And then I'm going to put this one in. There's another one at X equals 5. So E is a very simple thing to do. I like to do that first because then they kind of pop out to you. Because then you're looking at them, you're focusing right directly at those values, -3, +2, and 5. Okay. Now, if we look at A is asking us to focus on 2. So if we focus on 2 right there, it is not specifying a side, so both sides have to go to the same place. Are both sides heading to the same place? Yes, both sides are heading to -infinity. So that's our answer. Okay, now let's look at B. B is focusing on x equals 5. Are both sides going to the same place? Yes. What are they going to? +infinity. So that's your answer here. Now, C and D are asking from the left and from the right. The reason they did that, I'm assuming, is because they are not going to the same location, are they? At x equals -3, they're not. Now, from the left side, we are heading to a height of -infinity. That's what they're asking in C. But D is asking from the right side of -3, so we're coming in from that way. What height are we going to there? +infinity. So the limit as we approach -3 does not exist. The left side we can answer, the right side we can answer, but at that actual value of -3, we don't have a match. And they always have to match for the limit to exist. They always have to match for the limit to exist. Okay? Make sense so far? We good? Maybe? Any questions before I move on? Okay. We got, well, I don't know if we'll finish, we may have to finish our last examples tomorrow. So we'll finish these at the beginning of class tomorrow. So we'll continue with example 5. It'll just take us the first few minutes of class, and then the remainder of class you'll have time to begin the homework, which is at the bottom. Yeah.